All right, so now I'm working on question 4. Consider a proton that's in there's 2 boxes. So the first box is a perfect cube, 5 by 5 by 5. Well, the second box, box B, 3 by 5 by 10. So it's a rectangular box. So for both of these boxes, you're supposed to calculate the first 10 allowable energy values the system can have. Now the interesting thing is when you start getting to the first 10 allowable energy values, you have to calculate some quantum numbers a bit higher to make sure, because some of the ones that you think should be higher in energy actually end up being lower. So it can fool you a little bit, and I'll show you that in a minute. But this is the chart you have to hand in. One of these will be for box A, and the other will be for box B. So as complicated as this might look at first, it's a classic question that's done. So what we can do is take a look at the wave function for a 3-dimensional box. We start off with a 1-dimensional box, which only had this far, and B and C would be gone. So one of the ways I chose to do it is people would say length LX. I chose A as my L. X, B would be L in the Y direction, and C would be the length in the Z, right? So don't be confused. A is the length of the X, right? B is the length of the Y, C is the length in the Z. So this is the actual wave function, what it would look like. The energy, and this is what this question specifically wants you to do, the energy is simply whatever your quantum numbers for the X, Y, and Z are. H is Planck's constant. Other books might have H bar used with something different down here, but it doesn't matter what's H or H bar as long as you have the right one. 8 over m. This would be the mass of your proton right here, because that's what you're trapping in the box. So for box A, these lengths are all 5, right? So this would be 5 squared, 5 squared, and 5 squared. So you could almost say A, B, and C, let it just be L, which is 5. So I pull these A, B's, and C's out, called it L squared, because I know it's going to be 5. You would substitute in and calculate this right here. So the number I'm coming up with looks like 1.31 times 10 to the minus 24, and that'll be joules. So you're going to end up multiplying it simply by these numbers squared, right? Okay. The unit cancellation and stuff. This is how it all plays out when you're looking at the numerator and what the denominator is. So you guys can walk yourself through the unit analysis. It should look just like this, how this can come out to just joules, right? Not a bad exercise. So I think all we need to do for box A in the spreadsheet is just tap into that. So let's have a look and see what we get here. So in Excel, you make a sheet that has to look just like this. So you're going to have your quantum numbers, you're going to square them, and then you're going to add them squared, because that's what we just said you have to have. And then this will be the value of h squared over 8ml, which I think we already calculated, and you'll multiply it by what was in here. So I think I took that value that I already calculated by hand, and you'll multiply it by G3, which is this one. Well, G, right, and G, and then that's that. And then notice how this is in joules to the minus 24. So what this is asking you to do in the handout, there's the column in joules, but now you're supposed to put it in units of multiplied by 10 to the minus 23. So it's easier to look at, for instance, that value, 0.394, right? And so now you can look at all your energy states, and you want to find the first 10. Notice, for instance, you're going along and you might have had the quantum numbers 333. Well, that produces energy of 3.5. But see, the next one after that I was trying, which is a 3-2-1 state, is much lower. So you have to go through these and find the first 10 allowable. So for box A, what you're looking to do is take that spreadsheet and you have to hand in for box A. I just did this one by hand, right? So you can see how you have to find the value of the very lowest by number, what the first state is, and give me that. The next three are these ones, which is 0.78. So these are the first four states, 6, 7, 8. But you can see how this progression goes. You have to show me the lowest 10 states. Now these are degenerate, so somebody could even go so far as to say locate, even though you have 3 states here, but they're all degenerate with 1 energy value. So maybe this is the first lowest energy state, second, third, fourth, fifth, sixth, 7, 8, 9, 10. So you got to show me the first 10 allowable energy levels or states. That's box A. Box B, if I just go in here, you're going to do a similar thing, but with box B, it's going to get a little trickier. So you have the same thing going on, the exact same chart. You're going to have a different number for box B because the values were different. But you're going to get a lot more funky things doing. So what I've done is when I found the energy values, so obviously this one right here is for 111. That's number 1. So what I did is I made an extra column for myself. I located the lowest energy number I found. Number 2 is this one, 6.2, right? And then I ranked them so that I could show the first 10 allowable in order energy values. And then you would go over and list what the quantum numbers are. So for instance then, notice how the 10th energy state of 16.22, that's coming from 211. Right, but 2 in the x direction. So then you would turn around and make your next box B chart that would look like that. So in a nutshell, folks, it's not a difficult thing to do, but it clearly is an exercise in using Excel and mapping out the energy levels for a symmetrical cube and then a unsymmetrical rectangular box.